All right, welcome to the second week of Theory Seminar. Today we're very happy to have Haifeng Xu visiting us. Haifeng is an assistant professor in the Department of Computer Science, also affiliated with data science at University of Chicago. He finished his PhD in 2018 from University of Southern California, co-advised by Shadin Tukmi and Milen Tanbei. Milen's office was always so packed. So he just went to share an office with us. We shared an office for about 4 years because the theory group had fewer students back then. So his work has been recognized, winning best paper awards. Best paper award at WWW very recently, as well as a best student paper at Amos a while ago. And he's known for game theory, I guess, many work, but recently moving towards the intersection of game theory and large language models. And he's also a winner of AI 2050 early career fellow, something like that. I don't remember. All right, I'll give that to Haifeng.
Okay, yeah, so not important. Thanks everyone. Thanks for having me. Particularly, this really reminds me my PhD time with Yu. So great to come back and see him as well. So I know this is a theory talk, but so this talk particularly might be slightly different from kind of a typical theory talk where we show basic theory results and prove the results. So the goal for me today is actually try to illustrate a kind of an application domain, which is really important, I think. And I want to show you how actually theoretical thinking can actually help us to shed light on solving those important problems. So when you invited me, I actually debated a little bit whether I should give like a core theory kind of a talk or give this kind of a style. I realized that you guys already have a lot of core TCS talks. I thought maybe it's not a bad idea to show you a different perspective to think about the theoretical research. So that's hopefully I can kind of convey this message in this talk. So the title of my talk today is about rethinking online content ecosystems in the era of generative AI. So the kind of a motivation for this talk is really this recommender systems, which are already an indispensable component of our life nowadays. I can imagine that I don't do if I do none of them every day. I can imagine that kind of a day was like. So I have to access some of those. But not only because it's important to our life, but also this kind of content ecosystems or recommender systems are very important for the success of the modern generative AI, simply because those content recommendation system created a lot of online content data. And these are really crucial for the success for training those kind of large models, regardless in terms of text, in terms of videos, in terms of images. So because of these two reasons, and I think this really makes this a kind of a very important domain for us to study at this point. But of course, I'm not the first to study this. There's tons of work on studying these recommender systems. Particularly, there's even a computer science field. It's called information retrieval, which try to understand how you can do better recommendation, how you can do better ranking of those contents. And the classic research paradigm in this field typically is to say, oh, we have platform, which is the only kind of active party that's going to think about everything. So all the contents are just already existing there, or the users are already existing there. They're kind of a static there. And all I need to do is just trying to find a way to learn a good matching whenever the user comes, and to figure out what are the best contents to recommend to those users. So that leads to kind of a general thinking of this system try to learn or try to optimize this kind of matching in this kind of a static environment. And there's a lot of algorithms, really, tons of algorithms developed for this. How do we learn from noisy data? How do we learn from bandit feedback? How do we learn the best matching among those? And how to learn to rank those contents? Really a lot of research. So I think it's fair to say at this point, we're pretty good at learning those kind of preferences now. But the problem is why there are actually still pressing issues presenting in this kind of online recommendation system. For example, this is the kind of article from Nature was saying that this social media actually creates echo chambers for the information consumers, because we are kind of living in a bubble where the recommender system was creating for us. We basically only consuming information from those recommended items, and that reinforces our preference. We're just in this kind of an information loop. And of course, there's a lot of study about this unequal payments for this content creators. This is the article from Forbes, and this is another article from Nature, which was saying this actually content creators, or sometimes called influencers, tends to create like a polarized contents. The reason is very simple, because this polarization actually helps them to become more influential. And that kind of an incentive drives them to create this polarized contents. And you can see, merely just trying to maximize, so optimize the learning efficiency cannot help you to address those issues that are, motivated by incentive problems in the system. So, and that's kind of the core point. So while we are still facing these problems, because the pure learning theoretic approach overlooks the autonomy of the creators and the users. And that, this kind of autonomy is widely documented in the literature. Here's actually one example. So I think in the early years, YouTube trying to reward their content creators by like how long the viewers can look at your video. And because of that kind of an incentive, so YouTube immediately see that the people start to create longer and longer videos. And that you can see how creators are actually responding very actively to these incentives. Actually, so I'm going to cover a little bit about some live experiments we did at the Instagram over like a few millions of users on Instagram. And you can easily see there actually also the creators actually respond to your incentive change very, very quickly. Typically, after you deploy some kind of a change to the to their rewarding mechanism, you can see effects after 3 days, basically. And that's on the creator side. And on the user side, so those users are actually not static neither, because they actually have some explorative behavior, and sometimes they exploit by, depending on what are the few videos they saw in the past hours or something. And this kind of a behavior component were kind of largely overlooked in the classic, pure learning theoretic study as well. And that's really the motivation that motivates us to study, to kind of rethink about this classic learning, pure learning-driven paradigm for recommender systems. So therefore, the theme for my talk today is try to look at a kind of a different perspective to model this recommender system. We're going to try to do agentic kind of a modeling for both content creators, and try to understand the equilibrium outcome of this recommender system. So in a nutshell, we want to bring to the front about those people who created these contents, and try to understand what's the incentive for them to create those contents, and how can I steer their incentive towards a better content creation ecosystem. And therefore, instead of thinking of these contents as static, we're going to think of them as being generated by rational content creators. And then we try to analyze how can we design better incentive to drive their behavior for the better. And that is going to lead to multi-agent interactions, because those are all individuals who are in your system. And instead of in a static environment, we're going to see the evolving environment, because people are just acting and responding to the incentives. So that's kind of the overall picture of the talk. So in our group, we have actually also trying to study how you can learn from dynamic internet users when their preference shift. But that's not going to be the focus for the talk today. I'm going to simply view this internet users as a reward generating environment, and try to focus our study on this kind of incentives among the content creators. But if you're interested in the bottom side, like how you can learn from dynamically evolving users, I'm happy to chat offline as well. Good. Any questions so far? Okay. So this is my plan for the remainder of the talk. There were 2 parts. The first is I'm gonna show you a very simple basic model. Hopefully this theory audience gonna like to understand this, to model the current content ecosystems, and then to show how we can optimize those content ecosystems. So this is based on a relatively theoretical paper at the NURBS and also a recent KDD paper where we did a live test on Instagram over around 10 million Instagram users. I can tell you, I'm going to show you a little bit about what kind of results we got by implementing our algorithm on Instagrams. So the second part is more a kind of understanding level question. We're going to try to understand, because nowadays, generative AI has become a new way for us to create internet content. So we're going to try to see how human might be competing with this generative AI style of content creation, and what kind of long-term outcome we might be able to expect to see in this kind of a paradigm. That's kind of my plan for today. Yes, yeah.
That one slide, I don't think I quite understood this picture at the bottom. So what did you say about the users again? The reward generating environment. I guess I didn't understand if it's necessarily static or if it can be dynamic, even with this perspective that you're only really paying attention to the behavior of the content creators.
So in my model, I'm going to assume they have static preference. But ideally, I think you want to be more general. But I think that's probably that's a very good future direction, but not captured in the current talk.
Okay, but you could also have an intermediate case where you just assume that model is dynamic, even though you're not specifically modeling.
Oh yeah, that is right. Yeah, that's also a more general way than the way I'm going to talk about. Good. Yeah. Good. Any other questions? Okay. As a caveat, so it's definitely not that I'm not claiming that we solved the problem, but I think my goal is rather to show you examples where you can see how we can use theoretical thinking, particularly in my case, kind of algorithmic economic thinking, to shed a light on solving some of those issues and try to improve the system. Okay, so let's jump into the first part. So I will start with a kind of a very simple model that captures this kind of a content creation competition, or sometimes I just conveniently refer to it as a C3 because there were 3 C characters. So the model roughly is the following. You have a bunch of content creators. So this creator 1, creator 2, they have their own action set. So that basically captures, what kind of a contents you're good at creating. So maybe you are good at creating pop music. Another person is good at creating sports videos, or so on. And we have an internet user, which is drawn from a larger population. It actually doesn't matter too much to me that what F is, so long as you have like a population of users. So typically what happens on a recommender system is whenever such a user drawn from the population come, and then you can estimate the user utility. I mean, in typical recommender system, people call it a matching score. So what's what kind of a utility or how good this matching is if I recommend a sports or a basketball or recommend a soccer kind of a video. And based on this estimated kind of user utility, the system typically picks top K. In my example here, I pick the top 2 choice and show it to the user. And what this user is going to do is, of course, that's an estimated utility, not the exact true utility. So the true utility might be a noisy version of this one, which is why I have epsilon I, which is the noise added to the recommendation, to the estimated score. And the user is going to respond based on the best true utility. In this case, it's the second content. So the user is going to pick the second content and view this content. In this case, this is an important quantity. We're going to call this the creator 2's utility. And that is also the welfare this recommendation realized to the system. Right? And that's how much welfare you created by recommending the user, and the user kind of watched this video. Okay, and that's an important term that we will try to maximize because we want to make the user as happy as possible. And then there are this kind of self-interested agents in our system, which are basically the content creators. So each content creator's objective are basically try to maximize the welfare or maybe the happiness, but only for those attracted to this content creator, and minus some production cost. So here there were 2 terms. One is the welfare because of the user visited your contents, multiply the indicator function that the user indeed viewed your contents, and there was some kind of a production cost. So typically we need to assume this is the convex cost, but the detail of this C function would not matter to any of the results. Okay.
Convex in what?
Pardon me? Convex in the S2. Typically, we think of S2 as a real number because that's typically the embedding. In the real system, it's the embedding of the contents. Yeah. But for now...
So in a practical situation, what would S2 be?
So S2 mathematically is a vector, but in reality is actually a video. So every video has a vector embedding, which basically captures the properties of the video.
But then convexity would be kind of, why would something be convex in such a input?
So I meant convex in the real number. Okay, I think I would need convexity only for a later case, which I think it would be much more cleaner to see why it is convex. But for now, actually, it doesn't really matter what's the format for me.
Cost of producing the video.
Yes.
Right. So maybe the cost it gets like harder and harder. Maybe.
Right, but it's hard to visualize what this vector would be, right? But let's go on and we'll see better later.
Yeah, so we'll see it better. We'll see it better then.
Video, not like the quality of the video. Like
So
a higher quality video, I can imagine.
Let's let him move on because
for now, actually, it doesn't matter. So even it's not convex, so the first part of results holds always. In the second part, I need it to be convex, but it will be much more clear that why it is convex there. Good. They just suffer some cost for creating the contents. I just want to mention this kind of a particular utility here is roughly the rewards you got from the platform. For example, YouTube actually have a rewarding kind of a mechanism where, if you look online, there are a lot of YouTubers are sharing how much money they're getting. And currently, the YouTube's rewarding mechanism roughly proportional to like how much happiness you created for the internet users. But some of the other platforms actually reward based on how much traffic you got from the user. So it doesn't matter, your content was good or bad. It doesn't matter how many user views you got. So these are kind of a different incentive design for the content creators. Yes?
Can you be a little more specific about how they're doing that?
You mean for YouTube?
Yeah, like for example, how can I measure how happy a user is when he's watching my video? Like isn't the only information I have is like you watched which part for how long?
Yeah, that is right.
Watching them in a very bored manner or a very happy manner?
That is a little bit out of the scope of this talk, but I think YouTube researchers or engineers in YouTube, they have actually a lot of way to calibrate this kind of a behavior. I think they can detect some kind of a pattern where you skipped a lot of things. Yeah, there were details there, you can do that, yeah. But for the purpose of my talk, I was more just thinking of they have a way to evaluate the properness, and then I just view that roughly as the happiness of the user.
It is a very ideal situation in the sense that nobody cares about revenue, and I guess you just everybody believe long-term this is the right thing to do.
Oh, that is a very good question. So why YouTube doesn't care about revenue, but only care about the user happiness? Actually talk with the people there. Even like, I think Facebook at some point switched to the second prize auction because they want to do welfare maximization. I think the argument is that revenue is a short-term goal, but for this recommender system, that tends to be long-term, and welfare actually is a better metric, yeah. Yeah, and actually YouTube's, I think the revenue share system is basically how much, whatever money they get, they just share a fixed fraction with you as a YouTuber, yeah. Yeah. And from that perspective, it's natural to maximize welfare as well, yeah. Yeah, so that's the content creator's objective. And then this actually, we were basically talking about the platform's objective. So in the whole talk for today, the platform only cares about the system efficiency. So in other words, we wanted the system to create the maximum welfare, the most happiness for the population. What does the system efficiency mean? Well, it's simply the total utility for everyone, total utility for the creator plus the utility for the users. So that's what we care about. Okay, so that pretty much is the model, as you can see. So we can make it more general, as Amy was mentioning. What if the users are dynamically evolving? But for now, we are just working with this clean and simple model here. Okay. And this literally gives rise to a game, because every content creator was trying to figure out the best content to create. But of course, they need to compete with other content creators. If there were too many sports kind of content creation, then you don't have edge. So we're trying to understand how this kind of a competition evolve and what kind of equilibrium outcome we would expect to see. So the first result I want to show you is actually a theoretical result. So we're able to characterize the welfare inefficiency in this C3 game. So here's a statement. In any C3 game, if each content creator produces the contents via any kind of a strategy of no regret. So I'm a little bit hand wavy here, because for no regret, you need to think of a repeated setting. But for, just for those people who are not, not familiar with the concept, they just view this as a kind of very reasonable kind of a behavior. Basically saying you should do reasonable things. You shouldn't do clearly suboptimal stuff. So long as every content creator are doing this, then we can show that the accumulated total welfare of the system compared to the idealized maximum welfare. What does that mean? That means people are not selfish. You just control everyone, and you do a centralized optimization about their content creation. So the ratio between the two should be smaller than 1. But we can show that it cannot be too much smaller than 1. It's going to be at least 1 minus this kind of a threshold, which depends on one parameter beta, which is the variance of the people's choice noise. So basically, that's the the variance of the epsilon we were introducing, and the k is the number of recommendation slots. So you have 5 recommendation slots, k equal to 5. So that's kind of a characterization.
And can I ask?
Good.
If you were to calculate maximum welfare, idealized maximum welfare, that's taking into account the actual user utilities or their before noise utilities. You see what I'm asking?
Actual.
It's after, so it's based on the specific utility functions of the users after the randomness has been decided on.
Yeah, that is right. Yeah,
so
and then you are taking expectation over those. Yeah.
But it's interesting that the variance does come in here.
Oh yeah, that is right. Yeah, and the variance basically captures how explorative the user are. If the noise is small, user pretty much stick with the largest one. But if the variance is large, user are kind of a jump around. Yeah. Yeah. Good. And so this turns out to be the right term, because we're going to show there's a lower bound on this as well. So that's actually tight. Otherwise tight. There was some constant in front of it. Yeah. So for those of you in HGT field, this is actually a very classic concept called the price of anarchy. But this result is actually slightly stronger than the classic price of anarchy, because it's a quite a robust prediction, because we don't require every creator to be perfect rational. So long as you are doing reasonable kind of behavior, which is called a no regret, which captures a wide class of reasonable behavior. So long that's the case, then this bound holds.
I presume this applies when the regret for k stages is little o of k, meaning it doesn't have to be actually. Okay.
So no, he's asking when you say no regret, what precise? If you have t rounds, do you only require the regret to be little o of t, or square root of t? Or,
the regret has to be little o of t. Yeah, and that's why it can be hidden from this term, right?
No regret, we mean.
Yeah, that is right. Yeah.
Not much regret.
Yeah, not much regret. Yeah. That's why I don't have anything related to t there. Yeah.
But you're saying that t to the 0.99 is fine.
Yeah, it's fine. So long as your t is large enough, then it's going to disappear. Yeah. And this inefficiency, why it is not 1, but it's 1 minus something. The inefficiency comes from 2 sources. One is the selfish behavior of the creator. They're competing, so that's not as good as centralized optimization. But another factor is actually the explorative of the user choice, because a larger beta means kind of the user are jumping around more often. And in that case, actually, this price anarchy is actually become better. Yeah. Yeah, beta become bigger, and then the ratio will also become better. Yeah. So just want to show that this bound actually turns out to be tight. So there exists the C3 game where the price of anarchy is upper bounded by a term slightly worse than this one, but otherwise it can be tight if you letter k that goes to infinitely large. Yes. Oh, so this is I think this is a positive result holds for general behavior. This negative result holds even when the behavior was restricted to Nash. Because if you relax your behavior, you can make the bound worse. Yeah, that's right. Good. So the proof idea, actually, we employ this kind of a smoothness argument, which is a kind of a very well-known argument due to rough garden. But the proof here actually is quite involved because this is kind of a game have a new structure of this kind of a competition. It turns out that we need to analyze it to identify a lot of properties of this game, such as I think we actually show some submodularity of this welfare as a function of the number of participants. But it turns out that you can work out all those math through kind of derivations. I'm not going to show you the details of the proof here, but I just want to mention a useful fact. So this smoothness argument is a super powerful argument because whenever this smoothness argument goes through, your price of anarchy is intrinsically robust in the sense that it applies naturally to no regret kind of a behavior. But so that's pretty good. So right, if you can work it out, it's pretty good. But the bad news is actually there aren't that many games which admit a tight price of anarchy analysis using this smoothness technique. So to the best of my knowledge, I think there are only 3 very basic class of games: congestion game with a linear cost, and the second prize auction, and valid utility games. These are kind of very basic game models in the literature. And I think it's kind of interesting to see that this C3 game actually subscribes to this list because we are able to show this bound is roughly tight as well through a kind of a smoothness arguments. Yes.
I'm a little confused. If beta is bigger, which means more noise,
yeah,
then the lower bound is stronger.
Yeah, that is right. Yeah.
Right. So more noise is helpful to the ratio, maybe because it maybe hurts both the numerator and denominator, but maybe it hurts the denominator worse.
Yeah, that is right. Yeah, that is true. Yeah, that is true. Yeah. Good.
I guess the idea is, I'm guessing. I guess you're going to tell us.
Yeah.
But the point is, I don't have to be that competitive. Like if I'm a little bit worse than you, I'm still getting reasonable traffic. Then I'm happy there. I don't have to like spend additional effort to try to just be a little bit better than you. So I gotta get everything and.
That is actually exactly the reason for this term. And that also motivates our design later to actually better design the incentive where you can completely remove the term by better cultivate the competition among the creators.
Yeah, I guess I want the content to be recommended, right? Because otherwise there's no chance it's being clicked on.
Yeah.
As long as recommended, I actually don't mind as much because I'm a welfare person. So, if my content is shown but the user didn't click on it, then that's fine. That's not sufficient, right?
Yeah, that is right.
If it wasn't shown, then like if it's shown but the user chose something else, then that by definition is the right thing to do. That I don't care, but.
The welfare is only realized if the user watches the video.
Yes, but the user is realizing a higher value than my video if I'm recommended, right?
So you're happy with that?
As long as I'm
theoretically.
Yeah.
Okay.
Okay. Yeah.
Anyway.
Good. Yeah, I might need to move on, but so this result also shows some operational insights. The first thing is actually setting proper creator incentive matters a lot. So in my previous example, we're basically saying the creator utility is the true user happiness. That's in my model, and that's this value, and this basically roughly corresponding to the user engagement you are getting, and many YouTube actually rewards based on this. Some of the platforms actually rewards based on the if the creator utility is just the probability of being matched, and that's basically the user traffic. So it depends on how much user traffic got. It doesn't matter whether your content is good or bad, whether users are happy, so long as they came to your platform. And it turns out that in this case, you can show the price of anarchy term can be very bad. It can be upper bounded by half. This is not a surprise because the incentive are misaligned, but just something useful to note that you want to align the incentives. So what situations are bad for this, for this case? It turns out that actually have very interpretable kind of the bad example actually is very interpretable. So it's a situation where there's a dominating large user group with a lot of popular stuff, and there are a bunch of scattered niche kind of a topic around. And in this case, you can see at the equilibrium, content creator tends to or come to create this hot topic, and those people are actually ignored. And that's where the welfare loss was coming from. And that's the so-called trend versus niche kind of example. And that's exactly the lower bound example for achieving this. And also more recommendation slots definitely helps. More efficient the system is because a larger K gives you a smaller loss here. But of course, you say, OK, why don't I set K to be positive infinity? But the answer is that this K should be think of as the effective attention. It's not like you set it as infinity. People are going to look at infinity, many of them. It's really like how many people are going to look at. And we talked with the practitioners. Actually, they're saying this K roughly is 12 to 15, I think. So in other words, when you are going to the recommender system, very rarely you're going to see more, see the video after 15 this rank. So that makes us to think about, OK, if K equal to 12 or 15, this loss actually is a non-negligible constant. But we used to be kind of so when we presented this paper, this is ICML paper, I think. We presented ICML, and we actually happens to meet a bunch of researchers from Instagram. So they came to talk to us. They were saying we were kind of very happy with our result. We said, we have a tight bound. So and the loss was kind of negligible. So when they saw this, they were saying, oh, this sounds like it's like a 20%. If we can increase 5%, that's like a huge boost for Meta or for Instagram. And that really is the beginning of the conversation where we start to collaborate with them and try to further improve the efficiency of the system by hopefully getting rid of this term. And that's kind of initiated our collaboration with Meta, where we're trying to do mechanism design for incentivizing content creation. Essentially, we want to remove that loss term and get to the exact welfare optimal. So we again started with a theoretical analysis. So this is our original model. If you recall, in this original case, we basically reward based on the happiness you created for the creator. So that's how we rewarded the content creator. But if you really think about it, why you have to reward it this way, right? You can literally design whatever way you want to reward them based on, say, the matching score. It's up to you to decide how much you want to pay for the content creators. So therefore, the question we ask is, can we design or maybe optimize those rewarding mechanisms so that we can steer the or incentivize the creators' collective behavior for a better welfare of the system? So that's the next question we're trying to study. So we started by analyze why the current system's mechanism or reward mechanism might not work. What's the fundamental? Is there any fundamental issue with the current mechanism? And it turns out that we're able to theoretically characterize if your mechanism satisfies something natural, actually it will never be welfare maximizing. So there are two properties. One is, so if your rewarding mechanism are both individual monotone, which basically means if you as a content creator creates better contents, your own utility would increase. So that's pretty natural. And another property is called a group monotone, which means if your content quality increases, the total utility of the whole content creators is going to increase as well. So that means someone's quality increases, the total creator reward increases, this particular creator's reward also increases. If your rewarding mechanism satisfies this, then you can show that your mechanism would always have to lose at least 1/k fraction of the welfare.
It's the same K?
It's the same K, yeah, it's the same K. Yeah, I probably ignored some constants here, but roughly it's this order. Yeah. And the interesting thing is that both the user engagement and user traffic actually satisfy these conditions, because suppose some content creator have a better, have a better content, and then you just reward them based on how much engagement they got in total. And for this user, they should both increase in general. And that's why you should not expect those to be maximizing welfare, at least theoretically under the model. And therefore, many naturally kind of adopted mechanism are satisfying both as well. And that's, that's a theoretical explanation about why they might not be optimal. So, and that really leads us to rethink about the incentives in this recommender system. How can we design better incentives for them? So the idea we had is we're gonna overcome this limitation by drop the group monotonicity. In other words, if your contents become better, you will get a better revenue, but that doesn't mean that everyone in total together, the revenue gonna increase. Okay, and why that makes sense? Because that actually makes sense in economic markets. If you think about the monopoly market and the duopoly market, right? So if you have a monopoly there, the revenue is going to be very high. If there's another competitor come, the total revenue actually going to decrease. So you want to introduce competition basically to the market, and that's why that's what we're planning to do. And it turns out that if you drop that condition, we are able to design a new rewarding mechanism that's gonna maximize welfare in this model that I showed you. So the mechanism roughly is the following. So the core idea of the mechanism is I'm gonna reward the creator not based purely on how much traffic you got, but based on how much you are better than the next content creator. So there's a competition introduced in this rewarding mechanism. So the mechanism actually is very kind of clean to describe. Suppose we have 3 content creators. Their matching score is larger sigma 1, medium sigma 2, and a smaller 1 sigma 3. So the reward we're going to design for the creator are basically, so the mechanism are completely specified by 3 curves. It doesn't matter what the curve is, so long as one is above the other. So F1 is above F2 because sigma 1 is higher than sigma 2. And then the reward we're going to give for every content creator are simply the area of under the curve. So for content creator 2, the reward he got is basically the area of this blue. For content creator 1, who has the highest score, the reward is going to be the the area of all the blue region. So that's strictly larger. So what's the benefit of this mechanism? So the benefit is that the sigma 1, which is the highest creator, the reward actually decreases when his competitor become better. So for example, sigma 2, if it increases to be here, you can see the area actually becomes smaller. So this kind of a design basically introduces the competition to the game. And moreover, this design can also naturally accommodate the top K selection, because if you have more than K people, you can set the bottom ones the function to be 0. Therefore, the reward also be 0. So they will never be showed. So the theorem we can show that if you design the rewarding mechanism based on what I showed you, then this mechanism always induces a potential gain among the content creators. And that's something you can prove, right? And moreover, if you carefully pick those functions F1 to Fn, you can make the potential function precisely the system's welfare function. And there's a classical result in potential game saying there always exists a pure Nash equilibrium for the potential game that maximizes the potential function, which means it's going to maximize the system's welfare function as well, because we picked this function to exactly match the welfare function. Yes?
I forgot what do they mean?
So that's a part of the design.
That's the graph.
Yeah, but why do you get to pick them? Why is it natural for you to pick them instead of them being dictated by the
He gets to decide the page.
So yeah, I was looking at the question where I as a system can't decide.
Using these to choose your rewards.
Yeah, that is right. I have the freedom to decide how I reward everyone.
Right.
Yeah. What do they depend on? So this is an existence quantifier. Right?
Yeah, there is a way to find them actually.
There is a way, but
Yeah.
what are the inputs that are required?
So
What do
that was
those
the sigma.
depend on?
That was the sigma on the x-axis.
Yeah. Yeah, it depends on the sigma, the predicted score, and also the welfare function that we written out before.
I see. So does it evolve? Do the rewards then evolve over time as the functions themselves evolve as the sigmas change?
No, my model is purely static here.
Okay.
Yeah.
So in that case, F1 through Fn depend on static inputs.
Yeah, everything is static, depending on the specification of the model. Yeah.
But the meaning of sigma was the quality of
Sigma is the predicted matching score, like how good the matching is.
Utility.
Okay.
Yeah.
So match.
Yeah. Sigma influence is the estimation of the utility. Yeah.
So you need to estimate sigma. You need a content and a user. Both.
Yeah,
To know the
that
match.
is right. Yeah, that is right.
But you don't need those to get the Fs, right? Or you do?
Well, they're a function of the sigmas, which depend.
No, they're a function of the,
Yeah,
but the
right.
choice of functions. So.
No, I needed those two. I needed those sigmas to get the F.
I think Phil's question is how do you, the algorithm for computing F, what does that algorithm require as input? Is that a?
That's one way of putting it. Yeah.
Oh, so the algorithm was going to take sigma as input, where you can, from sigma, you can compute the welfare function. Because welfare is basically, so it's an expected welfare. So we know sigma is not exactly accurate. You're going to account for the noise, and there's an expected welfare. And then from that welfare function, you can compute this F. And then you decide. Okay. Yeah, we can chat offline as well. Yeah. Good. And so this was done with the, this is a theoretical collaboration with people from Meta. So we liked the result. So we're trying to see whether we can try to implement at least the, the kind of paradigms on this on Instagram. So, we talked with the engineer there, but it turns out that exactly implement this algorithm is almost impossible. So one thing is on this real system, we just cannot dramatically switch to a new reward mechanism because no one wants to be responsible for something like this, right? If you change something tomorrow, the revenue decrease, you're going to see this. So you cannot do any dramatic change. So that's a challenge. The second challenge is for Instagram particularly, we actually cannot arbitrarily design the reward. We can only tune the user traffic because Instagram actually do not have a kind of a monetary reward to the people. So they only kind of allocate the traffic for you where you can redeem that traffic to revenue by yourself. So it turns out that we're restricted in the design space to only control the traffic to people. And then we did a lot of kind of engineering kind of heuristics where we design a heuristic that follows the previous intuition, where the core intuition is basically introduce more competition among people. So if there are many content creators who are similar and competitive, they shouldn't get that much high reward anymore. And that's kind of the intuition embedded in the heuristic. And so that's in the design. And then in order to kind of make the change slow, we basically change the algorithm slightly, gradually change the algorithm, the incentive algorithm. And we also adapted the kind of a design to only tune the traffic without giving them like an arbitrary monetary payment. So literally at the end of the day, the true implementation was just some version of a multiple liquid weight updates heuristic. But you want to make it to encourage, discourage kind of too much competition, try to diverge people to different contents, basically. That's kind of the idea. And then we implement this algorithm around an 8-week A/B test on Instagram over around 10 million of users. So these are 5 million of internet users and 5 million of content creators. And we got actually quite encouraging result in the last 3 weeks. The first 5 weeks are less dramatic because our algorithm updates very slowly. So it's only after like around a month we start to see promising results. So the golden standard, at least on Instagram, for evaluating the system performance is something called a like-through rate. So that is when I viewed your contents, what's the probability I'm going to like that contents? So we actually does see around in total 1.13% increase on the like-through rate across different groups. These are basically different groups based on the size. And we also get impressions. The total impression of the contents are increased by 0.76% as well. And those are actually what the engineers they're saying that this is actually pretty significant improvement at this kind of a large scale. Originally, I was expecting 5% or 10%, but they were saying that was like it's almost impossible.
There's still time.
There's still time, yeah. So we also observed the improvement in other sides. For example, the impression actually had more diversity. So there's around 3.7% increase on the impression diversity of the newly created contents. And then there's a diversity on user consumption. So the user tends to look at the contents from more different topics, more topics, and the user-side engagement also increased for the newly created contents. Again, those numbers may appear small to the typical paper you saw, but we did talk with the people that these improvements are significant, even compared to their launched methods to their product. So that's kind of the first part I want to tell people about how you actually can start from the theoretical model and develop insights from the model, and then implement that insights in the real system. Though not as the implementation is not as theoretical as you wish, but I think the kind of insights you got from the model actually are quite useful. Yes.
And going back, I know the most important thing perhaps is the experimental results, but I'm just curious. This multiplicative weights approach sounds really appealing, and I wonder if you can go back and get some analysis for this method.
Oh yeah, we actually had some analysis in the paper, but I personally don't buy those analyses too much because the system was just too difficult to analyze. Yeah.
Okay.
Yeah.
No, I'm just thinking methodologically that kind of analysis might be relevant elsewhere. That's why I'm asking.
Yeah, that is right.
This
yeah.
is important to the work, but for purpose of method.
Yeah, that's a very good question. Yeah, we tried to do a little bit of analysis on why it works. We can show under some assumptions. I didn't show that's why I didn't show the results.
Are unreasonable or something?
Yeah, the assumptions I don't think are that reasonable. So the results are not as clean as I liked in the previous few results. But yeah, but that's a very good question. I would be really, really love to see, there's a more cleaner model that can demonstrate that this kind of multiplicative weight idea can work. Yeah. Yes.
Model to assume the cost of the content is the same across fields.
Yeah, so in general, this cost actually turns out to matter too much to this theoretical analysis simply because the number of contents are too large that I think many of the time it's more about what kind of content you can create. It's less about, how much time you spend on creating content. These are typically creators are less constrained by those costs, but they are more constrained by what kind of things I can create. Yeah.
In which case, the first creator, the reward now significantly drops, right? Because I am serving the same content.
Oh yeah, that's why everyone have like a domain for the content that they can create. It's not like everyone can create the same topic of contents.
If Akash is creating basketball videos, and then I also start just copy pasting all the videos he's creating, then his reward now significantly drops, right?
Oh.
You're serving the same content.
We didn't consider the copy pasting kind of a thing, which I imagine would be the platform would have ways to moderate those things. I would say, yeah. Anyway, so good. So I think in the second part, I'm just very briefly run through the kind of insights we got. So the model we're going to study here is pretty similar to the previous one, but we just have a generative AI playing an additional role there. So we're going to understand how humans competition with Gen AI. So pretty much the same model, except that we're going to think of the strategy SI as the total body of contents. But of course, this is not naively counting how many contents. You're going to be calibrated by the quality. So if you have a lot of contents but quality are low, that means your SI is going to be small, right? So it is calibrated by the quality. So the model is pretty much similar. So there's a population of user, and we're going to draw a user. Every content creator, I going to create an SI body of contents, and then they attracts a fraction of this user traffic. And that's basically the competition among the people. So the payoff here is the fraction of the content, the fraction of the population you got minus the cost. Here's a place with some convex cost. So it means you get more and more body of content, the costs are going to go dramatically large, which is natural in the economic modeling. And the creator here are assumed to be rewarded by traffic. I don't know what happens if you are rewarded by the engagement. We didn't study that. I think it's an interesting question as well. But up to this, that's basically the model we're studying. And by the way, this actually is not a new model. This is well known as the two-lock contest, which has been recently used to model the winning probability for mining Bitcoins as well. And there's a lot of political economy kind of application. We're just borrowing it here for modeling the competition among content creators. So so the question we're trying to ask is, what if generative AI enters the competition as a new way to create content? And how would that affect the, this equilibrium dynamics? So what we model is we're going to assume this generative AI, for example, some image creation, as a special creator who can create content, but the capability is going to depend on how many authentic contents human has created. So the power of the Gen AI depends on how many authentic contents human has created and multiplied by some parameter alpha and to the beta. This power law function was motivated by the so-called scaling law of the large models, where people actually observe as your model's performance as a function of the data set size, which is basically total authentic contents, is a power law function with some alpha and beta here. So that's a motivation for us to model this. And now we're just considering almost the same competition, but with the additional player here who is basically depending on the total creation by human. And then we can try to understand what happens in the long run at the equilibrium. And a particularly important question I want to understand is, will generative AI distort the human's incentive and maybe drive the human out of the system in the sense that the total body of human created content is going to have an orders of magnitude decrease. So that's the ideal case that I don't want to see. So we did some theoretical analysis, and it turns out that in our analysis, they will not drive human out of the system. They will reach certain symbioses. So the theorem we show is that if your cost function is a scaled L row norm, so that's an assumption. So that's a particular style of convex function where Wi is going to capture the creation efficiency of producer I. If Wi is large, that means your efficiency is actually low, right? Sorry, that means your efficiency is large because your cost was small, right? So the larger the Wi, the more productive you are. And then we have this vector of the productivity. So the result we show is that in this game, there is always a unique pure Nash equilibria. And moreover, at this equilibrium, the total body of human-created contents and the some norm of the human productivity, the ratio is always a constant between some lower bound and upper to some lower bound. And that implies that regardless even though there's a generative AI in the system, the total body of the contents order-wise will not decrease. It will just decrease by some constant fraction. So that's kind of the core message that we showed in the theorem. So that's pretty much the message. I think I'm going to just skip the details. So that's also going to be skipped. Yeah. So that actually brings me just to the summary. So we showed that there's a way to do multi-agent modeling for competing content creators among humans and possibly with generative AI. I studied this prescriptive question about how to optimize existing systems welfare, and also the descriptive question about understand the future of this content ecosystem under the trend of generative AI. And really the core is this picture where we think about content creator as rational agents as opposed to static agents. And there's actually a lot of recent works in this space. I didn't get time to survey the related literature, but actually if you are interested, there's a upcoming EC winter meeting where I'm actually going to give a tutorial there about where there I'm going to survey a lot of recent works along the space as well. Yes.
I booked a room for that whole day to watch all of these videos. If anybody's interested.
Yeah, so yeah, I'm actually gonna give a tutorial there about more other more related works in this space. And this year's topic is actually about the interplay of market design and generative AI.
March 6th, right?
March 6th, yeah, it's March 6th.
I'll email you.
Yeah.
Okay.
Okay, so I have some open directions, but that's pretty much it. I just want to thank my collaborators, particularly my PhD student who led this entire effort. He's actually on job market, academic job market, even though he was easily offered a meta offer by Instagram to continue this research. But thanks everyone, yeah.